Today I discuss one important topics related to inner product space. Okay, we write it here, inner product space. We also discussed inner product in previous class. Okay, today we discuss inner product space. This one is too easy. We also write it for definition. Okay, a vector space V, a vector space P over F. Okay, endowed with a specific inner product, with a specific inner product, endowed with a specific inner product is called an inner product space. Okay, then a vector space V over F endowed with a specific inner product is called an inner product space. Understood? Now we write it here. If F equal to C, then we call V a complex inner product space. We call V a complex inner product space. Complex inner product space. Okay, and far as F equal to R, okay, then we call V a real inner product space. We call V a real inner product space. Okay, we call V a real inner product space and we call V a complex inner product space. Understood? Now we also discuss here, that means P has an inner product xy and W is a subspace of P, then W is also an inner product space. Okay, when the same function inner product of xy is restricted to the vector xy belongs to W. Understood? That means if V has an inner product xy, if V has an inner product, V has an inner product, okay, xy, and W is a subspace of P, is a subspace of P, okay, then W is also an inner product space. Then W is also an inner product space. Inner product space. Okay. Then W is also an inner product space when the same function restricted, when the same function, okay, when the same function inner product of xy is restricted to the vectors, is restricted to the vectors, okay, xy belongs to W. Understood? Then what happened? We also erase that portion and going to further discussion of that. Okay. Now here m n cross n a. Okay, m n cross n a denotes the inner product space with the four Brownians inner product. Okay, is the inner product space. Inner product space with the four Brownians. Okay, four Brownians inner product. Understood? I think we also discussed Frobenius inner product. Okay, in previous class. This one is too simple. That means in this way we define, yeah, inner product of AB equal to trace of here B adjoint of BA. Okay, understood? Yeah, BA belongs to this one. Then we also discuss further one. Okay, that means some inner product spaces. In this way, we also discuss one important inner product space here. Here, inner product of fx cx. Okay, 1 equal to, we discuss it, 0 to 1 ft gt dt. Okay, and here we write inner product of fx gx of 2 equal to -1 to 1. Okay, here ft gt dt. Okay, our inner product on the vector space PR are our inner product okay, our inner products on vector space on the vector space PR on the vector space PR. Okay, then what happens? Then obviously we shows about that two inner product yield to different inner product space. Okay, that means even though underlying vector space is same. Okay, that means we also shows about that this one. Okay, this one's obviously that means gives one vector space. Okay, our inner product on vector space PR. Okay, then obviously we shows about that even though the underlying vector space are same, however these two inner products yield to different inner product spaces. These two inner product, okay, define to distinct inner product space. Inner product space. Okay. And then not a problem at all. We're also going to further discussion of that. Okay. Now we also discuss that means how this one are distinct. We also discuss now. Okay. Here fx and gx are polynomials, so polynomials coefficient from R. Okay. Here this one, that means how this one becomes distinct. We also check about that. Okay. So we erase our portion and going to further discussion of that. Okay. But we take here fx equal to x and gx equal to x square. Fx equal to x and gx equal to x square. Then what happened is here. Okay. here inner product of fx cx1 equal to what? Equal to 0 to 1 x cube here dx or t cube dt. Okay, understood? Not a problem at all, I think. Then what happened here? This one equal to that means this one equal to 3 to the power 4 by 4 1 by 4. Okay, and here fx cx, this one inner product of 2 here minus 1 to 1 t cube dt here t to the power 4 by 4 here minus 1 to 1 then 0. Understood? Not a problem at all. So this gives different values. Okay, so this shows that different inner product. Not a problem at all. Okay, so that means different inner products are also shows different inner product spaces. Okay, this one is confirmed, not a problem at all, I think. Okay, then what happened? Then here we also discuss another one, also known about this one. Okay, we erase that portion and going to further discussion of if in. We also discuss this one with respect to standard inner product. Okay, that means Fn we also discussed in previous class. Okay, Fn denotes the inner product space. Fn denotes the inner product space. Inner product space. Okay, Fn denote the inner product space. Okay, with the standard inner product. With the standard inner product. With the standard inner product. Okay, then what happened? We also discussed this standard inner product in previous class, but we write it in this way. Here x y equal to summation of xi yi I equal to 1 to n, and here x equal to x1 x2 dot xn, and y equal to y1 y2 dot y. Understood? Not a problem at all. So this one is too easy. We also discuss this one so easily. Okay, Fn denotes the inner product with the standard inner product, this one. Okay, here xy, what happened is here this one belongs to Fn. Okay, so in this way we also discuss, that means inner product spaces. Okay, so one vector space over field A with a specific inner product is called an inner product space. Okay, and obviously we also discuss further one. We write it here. Okay, how this one can become, then this one another example C01. We also discuss in previous class also C01. Okay, the vector space of real valued continuous functions of real valued, okay, of real valued continuous function of real valued continuous function. Okay, on 01 on 01. Okay, then what happened? Obviously, for if C belongs to C01, what happened? Define inner product of if G equal to 0 to 1 if T G T D. Understood? Not a problem at all. This one happened. So what we get here, this one is an inner product space. Okay, that means C01, the set of all real valued functions, obviously from inner product. Okay, this one, so we write it here C01. Okay, with respect to this inner product becomes an inner product space. Inner product space. Okay, this one example, and another one will also, that means write it in this way. Okay, here this example, that means C01. Okay, or write it another way. The the space, that means it's not C01 here. Okay, we write it in this way. The space age, the space age of continuous, okay, continuous complex valued function, continuous complex valued function. Okay, defined on 0 to pi. Okay, with the inner product, with the inner product. Okay, with the inner product, what inner product of fg equal to 1 by 2 pi, here 0 to 2 pi, ft gt dt. Okay, yeah, this one ft gt conjugate dt. Okay, then what happened is here, that means we also shows that this one is complete value function defined on an interval 0 to pi close with the inner product this one. Okay, here's some constant also here. This is not a problem at all. Okay, so in this way we also, that means write this one. Obviously we know about that. This one is important for here. Integration of if equal to, here integration of if plus integration of if2 and integration of if conjugate equal to integration of if conjugate. Okay, these two. Understood? So in this way we also then discuss this one, and obviously we now write one theorem related to that topics. Okay, so we erase that portion and going to further discussion one theorem. we write here theorem. Okay, let V be an inner product space. Let V be an inner product space. Okay, then for x y z belongs to V, or x y z belongs to V. Okay, and C belongs to A, and C belongs to A. The following statements are true. The following statements are true. Okay, first one. Here x y plus z equal to, here x y plus xz. Okay, second, here x cy equal to c conjugate xy. Okay, third, here x 0 inner product equal to 0x inner product equal to 0. D, here x inner product x equal to 0 if and only if x equal to 0. If x inner product y equal to y inner product x, sorry, x inner product z, x inner product y equal to x inner product z for all x belongs to V, then y equal to z. Understood? Not a problem at all. In this way, we'll also discuss this theorem. This one is too easy, I think. Not a problem at all. Okay. So we now just discuss first one. We have to prove it first. Okay. So we erase every portion and going to further discussion of that. Okay, this one gives this one. Okay, too easily we also do it by using the definition of inner product. Okay, now another one, option B. Here x c y equal to what? We write in this way. Here c y x conjugate equal to what? Here also this one. Okay, that means what we do here. If this one happen, then c y x conjugate equal to c conjugate y x conjugate equal to what? C conjugate xy. Understood? Not a problem at all. This one is too easily we do it. Okay. And in this way we also discuss those ones. Okay, it is that portion and going to further discussion that. Here x0 equal to 0, x equal to 0. Okay, we have to prove this one. X0 equal to what? Equal to 0x. Understood? And equal to what? Equal to 0 multiplied by 0x. Equal to what? Equal to 0. Not a problem at all. Similar way, 0x equal to what? X0 conjugate. Okay, this one is not needed here because if we write here 0 0 x, not a problem, and then this one is 0. Okay, in this way we write d. Okay, x equal to 0 if and only if and only x equal to 0. Okay, what happened is here x equal to 0, then what happened? Okay, this one equal 0 equal to, we write it in this way. Okay, this one we write it 0 0. Okay, this implies that what? This implies that x equal to 0. Otherwise if we write 1 1, then this one not becomes 0. Okay, so in this way we also write this one is 0. Okay, not a problem at all. And if we, that means if we want to modify this one, then obviously we write it here x0 plus 0x. Okay, this one equal, then x0 equal to what? 0. This one equal to 0. Okay, equal to 10 0. Then this implies x0 equal to minus 0x. Okay, and then this one implies what? This one equal to 0x. Then this one implies x equal to 0. Okay, in this way we also done it. And in another one is trivial. If x equal to 0, then what happens? 0 is 0, and this one 0. Okay, then x become what? This one is trivial. So we erase that portion and going to further discussion of that. Understood? Now we also write here. Okay, if xy equal to yx, or sorry, here not y xz, this implies for all x belongs to v, then what happened? Then y equal to z. Understood? And what happened is here, we write it now xy equal to hz. Okay, this implies that xy difference xz equal to 0. This implies x of y difference z equal to 0. This implies what? That means if x not equal to 0, That means for all x belongs to B, so x is not changeable. Then what happens? Y minus z equal to 0. If that means if x 0, then this one possible. If y minus z is 0, then this one possible. Okay. And if both 0, then this one possible. So x have not a problem at all. Okay. But this one, if x 0 or y minus z 0 or both. Okay. Then if x 0, then this one is possible. Then this one is trivial part, not a problem at all. Y equal to 0. Okay. But if for all x y equal to 0, then this x equal to 0 will not constant. Why? Because that means just x is not 0. If x is not, if just x is not equal to 0, okay. If x is not 0, then this one is becomes 0. Okay. Because for all x, this one holds. So this one 0 means I equal to 0. Understood? And obviously that means we want to write reverse. This one is not a problem at all. So today that means we discuss this one. Okay. And we also shows that which one, that means conjugate linear. Okay. Which one is conjugate linear? That means this one, this condition satisfied. Xy plus z equal to xy plus xz, this condition, and this one xcy equal to c conjugate xy. Okay. This one, if these two conditions are satisfied, then what happen? Then obviously we write it now. This the inner product is conjugate linear. Okay. In the second component, the inner product is conjugate linear. Okay. In the second component, in the second component. Understood? Not a problem at all. So in this way we also discuss this one too easily. Today we stop here. If you get this type of video, please subscribe my channel, please follow this channel, and obviously see this video. And if you want to give like, please click on like options. And if you have any question, comment, suggestions, write it in comment box. So today I stop here. Thank you.